Here's now the question is, I guess, do I even have PowerPoint anymore? It's like some kind of online thing now, right?
Yeah. We could go through the note well
Yeah.
at when it's 10. I mean 7 or
Yeah, okay. We can get started.
I don't know, just do the note.
Oh, that's funny. I never uploaded the things anyway. So.
Oh, right.
Okay. Oh, that's crazy. When you download the meeting materials, it doesn't have our intro slide. Ugh. Useless. Okay. Just bear with me.
Okay.
Just fetching the things now. Joint statement. Download. And floating scale. Download. Okay. All right. To desktop. Interim. Share slides. Okay. Is that visible?
Yes, it is. Perfect.
So now when I go to my thing here, it's going to block it. So let me try to share just the viewer. Okay, that works. Well, do we have somebody else from Les's team that can present?
I have to admit that I have not even looked at them yet. You know, the joint slides I looked at right away, of course, but the longer one I didn't look at. I mean, Bruno, did you want to do the joint slides or?
Yes, I can do.
Yeah, I think it'd be better since you're one of the other team guys than for me to go through them.
Yeah,
But
we could flip the order, right? Too.
Right.
So that Bruno could just present the joint thing and then do his presentation, and then.
Yeah.
I hope Les is okay. He doesn't usually.
Yeah. This is like one of those TV series where somebody goes missing.
Right. Okay. Well, let's go ahead and get started, I guess.
Mm-hmm.
All right, everyone. This is the LSR Working Group interim meeting focused on flooding optimizations. And we have a note well. Let me get my desktop in order. This is a standard note well. So it just says that by participating, you agree to follow the IETF processes. Any contribution make is covered. Well, you can read what's on the screen. Okay. And our agenda is going to be slightly modified because Les is not here yet. So we're going to start with the draft consensus. As AC called, we're going to start with the punchline. And then move on to Bruno's congestion control, flow control results from testing. And go back to Les, hopefully. And then we're going to have a wrap up with the discussion and next steps. Does anybody have want to bash the agenda at all? Okay. Turn the video on so you can see while I talk. Share. Yes. Joint statement. Okay, Bruno.
Okay, thank you for the slides. So a subset of authors on both draft met on Monday, and to discuss what we were the consensus on the points we were disagreement on. I would prefer less to be there, but Peter, please correct if I'm misspeaking. So next, please. So in fact, we agree on many points. We agree that many congestion avoidance algorithms are possible. I even believe it's written in both drafts. That algorithm is implemented on transmit side, sending side. We don't need consistency for interrupt. And hence anyone can do whatever it wants. So we don't need a real specification for that. part. Also, contrary to TCP, we don't have to be fair with other ISS speakers because we all under the same autonomous system, and also we're all saying the same thing. This is the same database in general, LSDB in general. So that's for congestion avoidance. Basically, anyone can do anything. For flow control, we need some end-to-end signaling to make it work between both ISIS speakers. I think we agree that it adds value, at least in some implementation, and possibly it does not add value in some other implementation, but it may be useful in summary. So the consensus is the best way forward is to provide a set of tools for implementation. And each implementation pick the tools that they want and do not use what they do not want. So next, please. So we plan to write a combined draft that would define a new TLV being capable of advertising some parameters, which could be the receive window, what we call LPP, which is the amount of LSPs we're going to acknowledge in a PSNP. Another one could be a partial Snp interval, so the amount of time between PSNP. Obviously, we made extensible to be able to advertise something else. And that TLVs would be supported in LOs on PSNPs. So this would provide a set of tools, but again, anyone is free to do and to use whatever they want, both on the sending side of the TLV and also on the receiving side of the TLV. Next one, please. So the draft could also discuss some algorithm, which would be non-normative. So provided as illustration or example. And we can also merge a discussion on the faster flooding. And basically that's all. We want to allow every implementation to choose on the best algorithm they want based on the constraints they have on deployment use case. So we plan, this is the target, to have a combined draft be published by IETF 112 meeting by a month from there. I think that's all. Next. Okay, so in short, we are not going to define any algorithm, whatever it is, but allow the advertisement of parameters to be used or not. Peter,
Yeah,
please correct me if it's not correct.
That was the last slide. Are you planning? So is this a greenfield? You're going to start with a new draft, or were you going to start with like your draft and just modify it?
The name would be a new, so it's a new draft. But obviously, we'll pick some existing text from existing draft, both of the draft.
Okay. Great. This is great news.
Yes, indeed.
Does anybody have any questions? Go ahead and pop up in the queue, or maybe just.
I was just going to say that hopefully we won't be relegated to the 5 offers. Although I'll volunteer to go to contributor on the combined draft. But I think this is a case where we should be able to let the main offers figure that out. And I know we have total probably 8 or 9 people. So, but Now, if I get off, that's still 8 people, which is over the limit, but hopefully we won't be relegated.
Well, who else is on Les's draft?
Peter, Tony P, and Marek.
Okay, so I'm going to pick one of those people to present if Les doesn't show up. If they're authors,
Right.
they can present.
They can, they can. I think, yeah, Peter or Marek would be, we're involved more with the testing than anybody, so they'd be the best ones.
Okay, well let's go ahead to go to Peter. You popped up there, but did you want to talk? Go ahead.
No. I was just going to say that I'm sure we can figure out who to put on if we are limited by the number of authors, we can fix that. It's not going to be an issue.
Yeah.
Okay, great. All right, well, Bruno, why don't we move on to your presentation then? It doesn't seem like there's a lot of questions on this, so I will load up the next one.
Okay, do you want me to present, or do you present? I mean the slides.
You can try to present, yes, if you would
Okay.
like to. Yeah, absolutely.
Well, I have PowerPoint animation, so.
Yeah, this is what interims are for, right? You can really mess them up. Grant screen. I have to give you permission somehow.
And I got some good news. Les has entered the Meet Echo room.
Oh, okay. Okay, I figured it out. There you go, Bruno. You should be getting the share now.
Yes, I do. Do you see slides?
Yes.
Excellent. So thank you. So I'm going to discuss results on highlights and the experiments we've done. So mostly Guillaume and myself on flow and congestion control. So 3 points, just a recap on the goals on the problem space. Then we'll focus on flow control. I will say why, and then we'll discuss the different modes of operation. So the goals, we want to be able to have faster flooding when the receiver has 3 cycles. We also want to be able to have slower floodings when the receiver is busy or congested for whatever reason. We want to avoid or minimize the parameters that the network operator has to tune. We'd like to avoid loss of LSPs. And obviously, we'd like to be robust, the algorithm to be robust to a wide variety of conditions, bad and good ones. So from our perspective, this is a 2-problem space. The first one is end-to-end. By that, I mean ISS process to ISS process communication. So control plane to control plane. When the receiver have obviously CPU limits and input queue limits. And the second problem space is everything else. So mostly it's communication from one control plane to another control plane. We have below a very simplified model. Obviously, it's implementation dependent. So we're not trying to discuss that. It's just everything else between one control plane and another control plane. And we believe that for these 2 problem spaces, it's better to have 2 solutions. So one is flow control, which is a control loop between a single sender and a single receiver. So really end-to-end between each ISS process. And the goal is to prevent the sender from overwhelming the receiver's control plane. Second solution is congestion control. It's to handle everything else. So everything else on the way. So it can be any resource. Again, implementation dependent. So for the purple one, congestion control, both drafts propose a congestion control algorithm. Is different, but the goal is mostly the same. There is no disagreement, I believe. We need one, and each sender is free to pick the one he wants. For the next one, for control plane congestion, we believe, I mean, on our draft, we believe that flow control is useful, and it's a key difference. So for draft Docran, we propose to use flow control with a receive window to handle the end-to-end flow control. And for draft Ginsberg, I believe they propose to use the same congestion control to handle everything, including control plane flow control. So since we agree, I believe, on congestion control, we will focus the presentation on flow control with a receive window. So again, it's control plane only. We want to avoid losing LSPs in the control plane of the receiver for any control plane reason. So it may be that we have reached the maximum throughput of the receiver as per its CPU, or the receiver is pausing because it's doing something else. So for example, BGP or PC computations or whatever reason. And so we're proposing to use a very classic receive window algorithm. So the receiver advertises a receive window, which is a number of LSPs that it can store in the control plane. And the sender computes the number of unacknowledged LSPs, which it has sent. We call it unact. And in short, the sender pause when unact is equal or greater than rwin. So it's very simple. We do need a new specification on interrupt. We need two things. We need to be able to advertise a receive window in either Hello PDU or PSNP. And also, we need to be able to have faster PSNP to get faster feedback in order to have a faster feedback loop. So from IETF 111, so in July, so we had some questions. So the window, receive window can be static or dynamic. There was some question about how does it work if the window is static. So I have a one slide to illustrate. So on the left, I have the sender of LSPs. On the right side, I have the receiver. So at the beginning, the sender is allowed to send some LSPs, the size of the window. So here in my case, for the slide, I have a fixed value of 10, so 10 LSPs. And when it has sent 10 LSPs, it has to pause. On the receiver side, well, he has to store those 10 LSPs. At some point, he's going to process some LSPs, let's say 2 LSPs. And then it will going to hack the LSPs with using a PSNP message, so existing PSNP message. So the sender on receiving this PSNP acknowledging 2 LSP, it can compute that the number of unhacked LSPs is now 8. So it can send 2 more LSPs. So it does exactly that. At some point, the receiver chooses to process some more LSPs, let's say 3, and same movie. It is acknowledging the LSPs in the PSNP, so usual message. The sender computes that the number of unacknowledged LSPs is now 7, so it can send 3 more LSPs, and so on and so forth. So here again, in this example, the rwin window is static, so it was 10 for the example. But the sender dynamically updates the number of unacknowledged PSNP by listening to PSNP and by tracking the number of LSP sent. And that way, we have dynamic flow control, even with a static receive window. So we believe this brings interesting properties because the sender pace and transmission pace is controlled by the receiver. So when we have n LSPs processed by the receiver, we have n LSPs act by the receiver by a PSNP, and then the sender can send n LSPs, but n is chosen by the receiver. Same thing from a timing perspective. The timing is decided by the receiver. It's when the receiver acknowledges the LSPs that the sender is capable of sending more LSPs. So in the end, the rate is n divided by t. It's fully controlled by the receiver. And if the receiver chooses to pause for 500 milliseconds doing BGP computation, the sender will have also to pause for the same duration, 500 milliseconds, without any new signaling. So really, the sender's behavior is driven by the receiver, and we use the regular PSNP signaling for that. So in summary, we believe RWIN with flow control provides interesting properties by design. So the sender cannot overwhelm the receiver control plane, whether it's CPU or input queue, because the sender has to wait for the receiver to acknowledge. Second point, the sender rate is completely controlled by the receiver, so it's aligned on its capability or performance. And again, if the receiver pause for any reason, the sender will have to pause. Same duration, same number of pause. So that's all for the theory. Now let's have a look at the operation modes that we can have. We can have three kinds of limits between sender and receiver. The first one is CPU bound, in which case the limitation is the CPU of the receiver. So for example, is limited by processing capability of 2000 LSPs per second. And that's all. Second option is we are limited by I/O transmission between control plane. So we have some loss of LSPs on the way, or some delays introduced because we are buffering, or whatever limitation. And a third limit, which is introduced by RWIN, by flow control, is to be RTT bound, because the rate is the rate that we can achieve is limited by the RTT. And by RTT, I mean control plane RTT. So this is the link delay both way, plus the time for the receiver to acknowledge the LSPs. And the limit is RWIN divided by RTT. So clearly, as the RTT increase, the rate that we can achieve on a given adjacency decrease. So let's have a look at the three limitations. So first one, I/O bound. So in short, it's not handled by flow control. In details, we have some feedback loops, but let's keep the details. And I think we all agree that for that, we have to rely on a congestion control algorithm. And we have one example in one draft, we have another example in the other draft, and anyone is free to pick another one on his favorite. So I don't think there is any fighting on that. Also, any sender is free to pick any favorite shaping option. So you're free to pick to send n LSPs every s milliseconds. It's purely local on the sender. So I don't think there is any disagreement or difference on that point. Now for CPU bound, and in our test, we found that in general implementation are limited by CPU, especially when you have multiple adjacencies at the same time. And the receiver also has to reflow the LSP it receives. Very quickly, you're limited by the CPU of the receiver. So in this case, where the receiver is CPU bound, by design, the flow control provides no loss of LSPs because the center is waiting for the receiver to be ready. It provides optimal rate. This is the one that the receiver can handle. And again, any pause on the receiver translates on the same pause on the sender. So we believe the behavior is optimal. And we have tested in different conditions, and that's what we have found. So I have a summary of 3 cases here. We're using 10 senders against 1 receiver. And we found that the overall capacity of the receiver is to be able to process 2,000 LSPs in general. So it needs to be divided by the number of senders. You may find it small or not, but it's a very old CPU. It's 10 years old. And we had 0 loss of LSPs, even though we had a competition between senders. So clearly, each sender is trying to send as much LSPs as possible, and there is no coordination between senders. So some are trying to force more packets, and it's very dynamic adaptation between senders. We have graphed on the behavior of each senders, and we can see the dynamic adaptations, but let's keep that. We also see that we are CPU bound, so changing RWIN does not change anything because we already reached the maximum capacity of the receiver. So that's all for our test. And without RWIN, we believe it's harder for the sender to adapt, and it may lead to loss of LSPs because the sender has to test the limit of the receiver, and sometimes eventually it will cross the limit. So depending on the algorithm, it may try to detect loss of LSPs or increasing delay or variation of throughput. But in general, you have to try and then you react after the receiver has paused or has decreased. So there has been some test reports, a few presented in IETF 111, and it shows that at least in July, so as per July status, when the receiver has to adapt without flow control, there is loss of LSPs. So I don't have experimental data to measure the loss of LSPs during adaptations, so typically some pause. But in theory, it should be around the sending rate multiplied by the delay of the feedback loop. So clearly, the faster you acknowledge, the faster you have a feedback, so the better. And minus the input queue of the receiver. So the receiver may store some LSPs that you cannot process, but at some point you will exceed the input queue of the receiver. So that's the benefit, very good performance for CPU bound. There is a drawback of RWIN, is that we have a new limitation of performance, which is RTT bound. It's very similar to TCP with long fat networks. There are some differences. So one is that for SIS, we're talking about one link delay, so it's not end-to-end across the internet. Another one is that all adjacencies, all communication advertise the same LSDB, same LSPs. So we don't really need to be fair. And it's less a big deal to drop some LSPs from one. And also, it's not a big deal if one speaker has lots of IRTT. It's okay if other senders have a low RTT, so we'll be faster with senders with a lower RTT. But again, we don't have to be fair. Third point, we believe SIS implementations to be typically CPU bounded, or at least that's what we found. Because there is some process on LSPs before acknowledging, compared to doing the work on the kernel. And one drawback is that the time to acknowledge will be longer for ISIS typically, because ISIS do some checks on acknowledge compared to TCP is being done in kernel. So that's the cost of the flow control proposal. But we believe it's a good trade-off for our opinion. But we do need a receiver to send faster PSNP. But we also believe everyone would benefit from a faster PSNP acknowledgement because it's a faster feedback loops, so everyone can have a faster reaction. So that's a conclusion. We believe the key difference is flow control based on Erwin. We're not trying to fight on congestion control. We believe flow control provides key benefits, which is when the receiver is CPU bound, we believe the sending behavior is optimal, so no loss of LSPs. We have the exact max rate supported by the receiver. On any pause on the receiver, doing something else, translate on the same pause on the sender. There is a key cost, which we do need a change on the receiver, which is to act faster than what is currently required by the ISO specification. And the second one is that the rate may be reduced for the neighbors which has a high RTT link. Otherwise, we need a high RWIN, same thing with TCP. And we believe both points are confirmed and quantified by the experiments. So last slide, next steps. So we believe that in many cases, the receiver is CPU bound rather than RTT bound. And we found Erwin to be very applicable. Especially, we have lots of links which have a low RTT. So links within cities, within a region, within a country, if your country is of a small size, so typically in Europe. Also intra-DC, you have a very, very small delay intra-data center. And so we believe our SIS implementation are mostly CPU bound. So from our point of view, we see no reason to forbid the ability to do flow control with Erwin. But for that, we do need a code point to advertise the Erwin. And hence, we are going to ask for working group adoption, either this draft or now we will move to a combined draft. Because we did ask a code point to ISI experts, and they refused because the document was not a working group document. So we have an implementation, and the feedback was we need a working group document for the code point. So that's all for me. Any question?
Yeah, I just had one. How did you determine that most implementations were CPU bound? Most ISIS implementations were CPU bound. I mean, I have much more experience, probably by a couple orders of magnitude, with OSPF implementations than ISIS, and I found them to be more IO bound. I know OSPF deals with much smaller units in LSAs as opposed to LSPs. Usually even the router LSAs are usually smaller. But how did you make that determination? That's just what I'm asking.
Okay, so good question. So clearly for our implementation, which was a free range routing on our server, we were about to track what was the exact reason for the performance. And it was not drop of LSPs on the IO path. It was just the sender being fuzzy. Another option is to see if you can, well, we did some of the tests with different implementations. All the ones who we are sourcing with a focus on Cisco iOS XR. We have less data because we can only look at debugging data. I'm not sure what I can say, but we found, but we can be wrong, that with current implementation, one big limitation is that the receiver is waiting to acknowledge the first LSPs, and that is just too late. So you have is too late in terms of he has a lot of LSPs in his backlog. It's too late. He can never come to the speed of the sender, and so it's CPU. It's not capable of acknowledging the LSP fast enough, and then at some point the sender timeout and send again the LSPs. For other implementation, we did not bother checking logs, so we are not sure. But in general, we would say that it appears to us that the receiver have to do some CPU work before acknowledging. But if you have a different experience, well, I trust you.
I was just wondering. Thanks.
But again, one correction: the limit is not when you have a single adjacency. It's when you have multiple adjacencies. So you have multiple senders, again, a single receiver.
So I have a question, a process question. You want to do a working group adoption. How is this affected by the idea of doing a new draft? I mean, it seems like it kind of doesn't make sense to do a code point allocation only to do a combined draft after that brings this in.
Yes, I agree. So it's the slides were done before we had the meeting on Monday.
Yeah.
So now the plan is to have a combined draft, and then we'll present, and then we'll see and ask adoption for the combined draft.
Okay. I mean, I suspect, I don't know, other people should come to the mic and talk, but I suspect that people are going to really like the combined draft idea. So I don't think that there's going to be a problem, but we'll see.
I don't know, but a priori, you will have less content in the combined draft because we restrict to common agreement. So yes, maybe less. Some people will not be happy with the lack of detail. Maybe we'll see. We'll see.
Yeah, we'll see. All right. Anyone else? All right, Bruno. Well, thanks a lot. And
Thank you.
Let's move on to Les.
I was just going to make a point that I looked at looking at the participants. We have a lot of the people that are going to have an opinion on this anyway in the meeting, with the exception of possibly some of the people in the China time zones.
Yes. Are you there, AC? Okay. All right. Well, I'm going to share Les's presentation.
All right. Can you hear me?
I can hear you, Les. Let me share the your presentation unless you have it handy.
I could, but
No, it's
you know,
no
what,
no big deal. Bruno did his, and that was nice, actually. But let's see. Here we go. Share. There we go. Okay. See.
okay. First, my apologies for being late. I'll have to speak to my secretary who messed up my calendar. All right. Okay, next slide, please. Some of this is repetitious from IETF 11, but we have there hasn't been an update to the draft, but we have done some additional test results, and that's been incorporated into the presentation. And also have some other slides that cover some other material. Next slide, please. I'm sorry, Chris, could you go back to the previous slide? One of the things that we realized after the meeting, the last meeting, was some of the testing that we had done when we paced the receiver, that we limited the receiver to being able to process X number of LSPs per second, was that the way we had implemented that was the receiver was simply dropping any LSPs beyond the arbitrary limit that we had introduced in our test code. So effectively, we were testing the congestion case. So one of the additional tests that we've done now is we've tested where the receiver is not dropping, but they're just processing LSPs at a slower pace. And you'll see those results as we get to them. Next slide, please. So this is the same slide we presented previously, just kind of an overview of the algorithm guidelines. We understand that flooding burst durations are not long-lived. For example, if you have a node with 2,000 neighbors and it goes down, so you have 2,000 LSPs that need to be flooded. If we're flooding even at a, shall we say, a modest increase over the current rate at 300 LSPs per second, this is going to take roughly 7 seconds. If we're going to adapt, we need to adapt relatively quickly. Otherwise, the burst period will have gone by, and we won't have been able to make any adjustments. We understand that receiver performance can vary from time interval to time interval because of a variety of factors. We'll go into a little more detail later in the presentation. And if what we want to be able to do, and I think this is certainly the same goal that Bruno has talked about, is we would like to minimize retransmissions. And since standard retransmission timer is 5 seconds, that means we'd like to be able to make adjustments in less than 5 seconds. The algorithm tries to do a very aggressive slowdown when we think that the receiver is not keeping pace. When the receiver is keeping pace and we want to try to increase, we do this much less aggressively. The last point is probably one of the most important. We know that it's going to take a long time to deploy any new feature in a network, and we would like to be able to take advantage of faster flooding in the presence of legacy nodes. So we have to understand that receiver may have been optimized to send X more quickly than it does today, but it may not. The receiver may be, or we may be in a network where we've used some of the new flooding optimizations, such as parallel link suppression, dynamic flooding. Receivers may or may not have optimized the priority of packet processing. We'd like to be able to safely use faster flooding, even in the presence of legacy nodes that don't have all of these new bells and whistles. Next slide, please. So our proof of concept algorithm that we've implemented in our testing, what we do is we track the rate of transmissions over a multi-second history and compare it to the rate of acknowledgements that we have received. We've got two configurable parameters. One of them is simply the absolute maximum that we will try to send. And in order to track accurately whether the receiver is keeping pace, we need to know what the PSNP delay is. By specification, 10589 suggests 2 seconds. Implementations today may be using 2 seconds, they may be using 1 second, they may be using something much shorter. Knowing what the acknowledgement delay of the neighbor is important to the accuracy of the algorithm. Currently, we're using this as a configurable knob. I think in the combined draft that we're talking about generating, this is a candidate for being advertised by the receiver. So you won't have to configure it. The receiver can actually tell you what it's doing. So we've incorporated the neighbor-specific ACK delay into the algorithm. And we don't really care why the receiver is not keeping pace. It could be because packets are lost from the transmitter. It could be they're lost on the receiver. They could be corrupted on the wire. There could be issues with the punt path to the control plane. There could be CPU issues. We don't care. We just track, is the receiver keeping pace with the rate that we're sending? And if it's not, then we're going to slow down. The term that we use in the presentation for current LSPTX max is the current value that we're using to flood to a particular neighbor. Next slide, please. So here's the simple setup. We have a emulation of a network so that we have 2000 LSPs. We have the UUT, which acts as the sender, and we have another box that is the receiver. We reset the receiver, which triggers the adjacency bring up, and we have to flood all 2000 LSPs. For most of our tests, we've optimized the PSNP delay on the receiver so that it's 1 millisecond. And we have test code on the receiver that manipulates the rate at which the receiver processes the incoming LSPs. And we have two modes. Like I said, in the original testing we had done that we presented previously, the receiver simply dropped whatever was in the queue that was beyond the arbitrary processing rate that we had set up. But we've now tested with another option where the receiver doesn't drop the LSPs, he just doesn't process them until until the next second. If we say we're going to process 100 LSPs per second, when we get to 100, We wait until the next second occurs, and then we continue processing. Next slide, please. If we're sending at LSPs at a high rate, the simplest scheme would be to say, well, okay, if I'm sending 100 LSPs per second, let me send one LSP every 10 milliseconds. If I'm sending 1,000 LSPs per second, let me send one LSP every millisecond. But this is not a practical way of doing things, because in a real environment, ISIS is not going to get to run every millisecond, and it's certainly not going to get to run necessarily at a completely regular interval because of contention for the CPU. So we do LSP transmission bursts, and based upon our current transmission rate, we are going to limit the number of scheduling intervals where we're going to schedule transmissions. And then on each scheduling interval, we'll send a burst of whatever, 5, 10, 20 LSPs in order to follow the current LSP TX rate. We refer to this method of transmission as optimized, and you'll see that in the test results. Next slide. So this is baseline testing, where we have 2,000 LSPs. There's no limit on the receiver. The receiver simply processes things as fast as they come in. And we're not making any adjustments to the rate at which we send LSPs. So this is pretty straightforward. If you send things at the rate that most implementations do today, which is roughly 33 LSPs per second, it takes about 66 seconds to send all of the LSPs. If you send it at 1,000 LSPs per second, it takes a little under 2 seconds for this to complete, and so forth. Next slide. So here's a test that we did where the receiver, for whatever reason, is unable to keep up with the pace of LSP transmissions. So in this test, we had a processing rate of 100 LSPs per second on the receiver. So if we're only sending at 33 LSPs per second, then the receiver can keep up. It still takes 66 seconds to get all of the 2,000 LSPs exchanged, but we have no retransmissions. If we simply send roughly 300 LSPs per second, but we don't use our optimized transmission scheme, so we're basically sending this every 33 milliseconds, every 3 milliseconds, I guess. We get done faster, but there are a lot of retransmissions because the receiver is not able to keep up. If we use the optimized scheme, and these next two lines are using the method where the receiver simply drops whatever is in his input queue past the arbitrary rate of processing 100 LSPs per second, then you can see the duration, and there are significant retransmissions. This is equivalent to a congestion case. The two lines that are highlighted in green are the new tests that we ran since IETF-111, where the receiver is not dropping the LSPs, it's just processing 100 per second, and then the next second and process another 100. And what you see in the case of 100, where we start with a rate of 300 LSPs per second, is that we adjust down to 100 LSPs per second, and we're able to react quickly enough that there are no retransmissions. In the case where we started with a rate of 1,000 LSPs per second, and the receiver is not able to keep up, it takes a bit longer to complete the transaction, and we do have some retransmissions. The retransmissions are due to the receiver processing delays, and by that I mean we start out by sending 1,000 LSPs per second. The receiver at this point in time is only able to process 100 per second. So in the first second, it gets 1,000 LSPs. It's not going to be able to acknowledge all of those LSPs before the 5-second retransmission timer expires. And so we do end up with retransmissions. Most of those retransmissions are redundant, but of course the transmitter doesn't know, and it's just a matter of it takes a bit longer for the adjustment from a much higher rate to the much lower rate. I think if you go to the next slide, we have graphical representations of this.
A clarifying point here. You've modified the receiver to be able to put the rate in that it will drop at, right?
Correct. Correct. There's test code on the receiver that just arbitrarily says, hey, after I've processed 100 LSPs, I'm going to stop and wait for the next second. But the LSPs are still in the input queue. So what you have on the left-hand side is the transition from a 300 LSP per second rate to a 100 LSP per second rate. And you can see that we decrease rapidly, and we're actually matching the consumption rate of the receiver in less than 5 seconds. And as a result of this, there are no retransmissions. In the case on the right, we've already sent 1,000 LSPs in the first second or two, and they're not going to get acknowledged. It's going to take up to 10 seconds for all of those LSPs to be acknowledged. But we do drop down to the receiver rate within a few seconds, and we then match the pace at which the receiver is able to process the incoming LSPs. If you go to the next slide, so this is the same test, but the receiver now is not dropping the LSPs. It's simply buffering them in its input queue, and it'll process them as it catches up. And again, you see here that we quickly match the consumption rate of the receiver. But again, in the second case, there is going to be some redundant retransmissions simply because the acknowledgements did not come fast enough. Next slide. This is, I think, a less interesting case. It just shows what happens when the receiver has a consistent receive rate, which we've already adjusted to. In other words, our target LSPTX max is either 300 LSPs per second or 1000 LSPs per second. But based on previous performance, we've already adjusted to the receiver rate, and we continue to send at the rate that the receiver is able to consume. And as a result, it takes roughly 20 seconds to send the 2000 LSPs, and there are no retransmissions. Next slide. This is just a graphical representation of that table. The next slide. So here's the case where the receiver is able to consume LSPs faster than it did before. Remember that we're less aggressive when we speed up. So in the case where we were sending at 100 LSPs per second, but the receiver is capable of consuming at 300, we ramp up, and you'll see that in the graphical presentation of this. So we end up taking roughly 11 seconds to send the 2000 LSPs rather than 20 seconds, which would have been what it would take at the initial 100 LSPs per second. When we're ramping up to 1000, it takes, because we ramp up more slowly, it takes us longer to achieve the maximum rate. And so it actually takes 2 bursts. At the end of the first burst, we're not yet at 1000. It takes another burst of 2000 LSPs in order for us to realize that the receiver is actually capable of maintaining 1000 LSPs per second. So if you go to the next slide, we have a graphical representation of this. Again, the graph on the left is ramping up to 300. And as you can see, we ramp up to 300 before we've sent all of the 2000 LSPs. But in the case on the right, where we're trying to ramp up to 1000, after the first burst of 2000 LSPs, we've ramped up to roughly a little under 600 LSPs per second. And then when we trigger a second burst, we'll continue to increase since the receiver is able to consume at the faster rate, and we'll eventually get up to our configured maximum. Next slide, please. So our future plans, we're looking into, we've got a number of internal parameters that we can tune. As we're looking at, clearly in the case where there's a steep slowdown that we were sending at 1000 LSPs per second, and for whatever reason the receiver is now only capable of 100, we've seen a number of retransmissions. We're looking to reduce that by adjusting some of our parameters. And probably far more important is obviously the testing environment that we presented is a very simplistic one. We need to look at what's happening when you have a larger network, you've got multiple neighbors, the UUT is not only sending LSPs, but it's also receiving LSPs. And this is what we're engaged in now as far as our testing is concerned. Next slide. All right, this is a sort of a picture of a abstract router architecture. It's not representative of a particular router. It's representative of many of the routers that certainly I have worked on, and from discussions with other people, I think it's also representative of other router architectures. So what you have here, you have a line card, and a router may have one or more line cards. Each line card has a set of interfaces. As packets that are destined, for us processing for whatever reason, in our case, we're obviously interested in IS-IS packets, but There are OAM packets, there are BGP packets, there are many packets that are going to be punted to the control plane for processing. So there are a number of packet queues that each of the interfaces funnels incoming packets to based upon packet types. There may be one queue, there may be 10 queues. It depends upon the specific router implementation. So each of these queues has some subset of the 4OS packets filtered based upon things like an LPID or your TCP port number or other aspects of the packet. A particular queue may be dedicated to one type of packet, just ISIS packets, or it might have a variety of packets going into that queue, for example, all routing protocol packets. Within that queue, if there are multiple packet types, there may be limits on how many of a given packet type are allowed into that queue. Lots of variations in this. Next slide. Same picture. This is only talking about the next stage is from all of these incoming packet queues. We need to put them into a punt queue to be punted to the control plane. And again, there may be controls put on, there's obviously controls on the size of the punt queue, on how many packets from each of the input queues, what the rate is that they go into the punt queue. Next slide, please. So this is looking at the control plane. So from the control plane, we've now got an input queue, which is the input from the punt queue on all of the line cards. That queue now contains packets of a variety of types. Again, we're primarily interested in ISIS here, but there could be OAM packets in there. There are TCP packets in there. There, whatever has been punted. So we need to take those packets and put them into another queue that is specific to the particular packet type. In our case, we have an ISIS input queue. Note at this point, we have packets from all interfaces on all line cards, or at least all the ones that are enabled for ISIS. And we have all ISIS packet types. We have hellos, we have SNPs, we have LSPs. We may be running one instance of ISIS. We may be running multiple instances of ISIS. So we now need to separate out from this input queue those packets which are for ISIS instance number 1 from those that are destined for ISIS instance number 2, and so on. Again, at this stage, we still have all ISIS packet types, hellos, SNPs, LSPs. At this point, implementations have various strategies for this, but one of the things that's often done is we like to prioritize the processing of hellos over SNPs and LSPs so that adjacencies are less likely to flap under load. So we may move the hellos into a separate processing queue and put the SNPs and LSPs into another queue. And again, the implementations may vary. They might separate SNPs from LSPs, variety of strategies here. Next slide, please. So the sum of all of this is you have to look at, what is the state of the receiver at a given moment? In other words, how can I determine whether I'm in a congested state or not? Well, I've got these policed input queues in the data plane. I've got the punt queue. I've got the control plane input queues. What is the state of all of these queues? In order for ISIS to accurately signal its current state to its neighbors, you would have to understand the state of all of these elements, and would also have to do this in real time. Because as we discussed, the duration of a burst is not going to be a very long time. It may be a couple of seconds, it may be 10 seconds, it might be 15 seconds. If we're going to respond accurately, we need to be able to track this and report this to our neighbors in sub-second time. And we need to be able to map this performance per interface. Next slide. There are obviously a lot of other factors that affect the performance of the receiver. How many neighbors do you have? What's the size of the network, which affects the size of the LSP database? Whether you have flooding optimization supported, what other features are running in the box, what is the CPU scheduling, do we have multiple cores, do we have a single core, hardware speed and memory, etc. Next slide. If we're going to signal this, the signaling is required when a flooding burst is happening. Most of the time, when the network is stable, our level of flooding is minimal. We're just doing refreshes, which are quite modest. During a burst, both the transmitter and the receiver are going to be very busy. They're going to be busy doing the ISIS work. They may also be busy doing other work, which is a side effect of whatever the network topology change is. The node may be receiving LSPs and sending LSPs. The methods of signaling are going to be either hellos or SNPs. They themselves are unreliable, so they could be dropped under load. These kinds of delays will increase the likelihood of retransmissions. So the gist of this is, in order to adapt, we've got to adapt quickly. If we adapt 10 or 20 seconds later, that may help us for the next burst, but it's not going to help us with the current burst. Next slide. So the summary of all of this is that accurate real-time signaling of the current state of the receiver is challenging. And that's kind of the main reason that we've decided in our approach not to depend upon it. We're only depending upon the actual rate of ACKs that we receive from the receiver. We don't care why the receiver is not keeping up. We just adapt based upon what's actually happening. And I think this is the last slide.
Yes, it was. Well, I since I'm talking, I have a comment on this. What you just talked about. The signaling, if I'm not mistaken, that's been proposed so far, whether it be the RWIN or even the one that you were talking about, the Snp interval, both of those are static values. So it's not something that would have to be signaled, during a burst.
Well, so I'm not the RWIN advocate, so probably Bruno should respond to this, but I do believe that for RWIN to be most useful, it needs to be dynamic. Otherwise, the alternative is that you pick a conservative value that you think is safe even under the maximum load conditions, and then you don't achieve the highest throughput that you might be able to actually support.
So I used to think the same thing when I was just sort of looking at it at a high level, but in fact, if you break the queues down per adjacency, it is, you can give it a static value, right? The reason that you're thinking that needs to be, and I thought that it needed to be dynamic, was to adapt to the network conditions, right? But if each adjacency is given, 30 queue slots, each neighbor has its own queue and it's 30 big. Your R-win's 30, right? No matter how many neighbors you have.
So the routers that I work on are not implemented that way.
That's a software issue.
No, it's not just a software issue. This
Well,
is
I've worked on the
largely a
exact same software you're talking about, and in fact, I worked on the CLNS input queue stuff, right? And you can make modifications to that software to queue per adjacency. It's not hard. It's just software.
So Chris, I mean, I think there's many comments that could be made here, but if you go back to the slides that represent the data plane, you're talking about what's available to the control plane, and we might still have a debate about that, but you're not talking about what's going on in the data plane, and that's not so easy. That's not so easy to change.
You're correct, but that's conflating the issue, right? The R-Win is just talking about how much the receive queue for ISIS for each adjacency. Yes, if you want to bring everything together and talk about BGP traffic and all that other stuff, you've got to do some other things, right? But we're just talking about R-Win being static.
So let me just make one comment, and I think Guillaume and Tony probably have much more to say about this.
Yep.
But if you're trying to determine the state of the receiver, and you want to know whether the receiver is getting overwhelmed, you cannot just look at the input queue to ISIS. You have to look at the state of the router as a whole. You might be dropping packets in the data plane, and ISIS in the control plane has no idea this is happening. And as far as ISIS is concerned, he's going, "Oh, my input queue is half empty. I'm cool."
Correct. This is why it's good you guys are getting together, right? I'm not saying this is black and white or you have to choose one. Your approach is dealing with the overall, congestion that can happen. The R-Win is doing something else, which is saying you can send me this many LSPs and I won't drop them, right? And it's just another way to optimize the situation, right?
All right. I mean, let me let Guillaume and Tony go ahead.
Guillaume, go ahead, Guillaume.
Yes. Hello, everyone. So I wanted to go back on the R-Win. So you said that R-Win needed to be dynamic, and I think that yes, when you want to do congestion control, you absolutely need a window that is dynamic. But you can actually do both. Use the advertised R-Win as an upper limit on what your allowed window on the receiver side is allowed to go. For example, a receiver advertise a receive window of 100. If the senders just uses directly this 100 receive window, the problem is that there could be losses before the input queue, just as Les explained. So it's cool if you don't want to lose packets at the input queue. This is a first guarantee, but it's arguably not enough. And for this, the idea is to go from a very small window on the server side, and with the ACKs you receive, you can infer if there was congestion or not. So for this to work, obviously, you need very fast PSNP. So ideally, one PSNP per LSP, so that you are able to infer if there were packet loss before the input queue of your router. Does that answer your question?
So, Chris, I think Guillaume's asking you, I think.
Yeah.
No, I didn't have a question.
Oh, but yeah, okay. I thought you were asking, do we need the R-Win to be dynamic?
No, I don't believe you do.
Oh, okay. Well, I tend to believe it's better if you indeed want to avoid losses in between. But yeah.
Yeah. Okay. So, I mean, I did a picture, right? The green ones are the queues per neighbor. That's all I'm saying is Arwin in this case is 5. But Tony, do you want to go?
Yeah, I just wanted to chime in as another evil, greedy vendor. Implementations are all over the map right now, and hardware has been making great strides in making interesting progress. That said, there are a whole lot of implementations that are not particularly elegant, that they comply with the first model that Les showed with a giant punt queue and everything just funneling into that punt queue. Now, there's more complications. The things that funnel into that punt queue are rate limited. And so even though the queue may be 10,000 packets deep, you can only dump 1,000 packets per second into it or something, and the hardware is not very forgiving about that. And maybe you can program your punt queue rate or not. Whatever it is, it's a messy, messy business. There's no question about that. And the number of software-only implementations out there that I've seen are pretty slim, although thanks to containerization and people doing software as a service, yes, we still see that too. So again, we've got an enormous amount of variation we have to try to capture. And Arwin is only a first approximation. And maybe over time we learn better ways of doing things, but the whole point is to give us some mechanism, because we realize that some feedback in the control loop is better than no feedback.
AC.
I just want to say we really don't want, because of all these implementations, we'd really, I mean, this is going to be this draft, this isn't going to be a draft that's a hammer that says you must do this and you must do that. But I'd encourage implementations to allow speed up without the receiver sending RWin. You know, that you could have a way to bypass that or statically configure it, so you don't depend totally on the RWin.
We are completely agreed that Arwin is wholly optional.
Yeah, but okay. And the other thing I was going to say, anybody who has a rate limit on their punt queue or queues without doing it without some classification, I mean, that's just, that would just be very naive anyway. I don't think there are any implementations that don't do it, that rate limit just arbitrarily on the punt queue and don't do it by packet types or by classification. So
Merchant is not what you want, it's what you get.
Okay.
Right.
Yeah.
But to be fair, I mean, some of these, most big routers will, you know, do some amount of classification. Even in the MPU, you know, you've got an ISIS packet. But yeah, like Tony, I think your point is well made that you know it's all over the place, right? And I certainly wouldn't argue against trying to deal with that you know situation. But I don't think we should limit ourselves to the lowest common denominator either.
Why Arwin makes sense for the cases where you can get additional useful information.
Yep. All right. Les.
That came out of our consensus on Monday was, and you know, I think, you know, Tony's probably the one who voiced this, is, you know, let's just provide the tools that are needed to support a variety of strategies, and over time we'll find out what works and what doesn't work. And you know, people may still, you know, maybe 3 years from now, we may still have people who prefer one approach over another, but at least we have the tools to support a variety of strategies.
Absolutely. It's a great outcome, I think, this meeting you guys had.
And we also know that we're still learning about TCP mechanisms. So, to think that we're going to get this right on the first pass is nothing but arrogant.
Yeah. Okay, AC, we had, I'm looking for my agenda here. We had discussions and next steps. Looks like we're at the end of discussions.
Yeah, I think we're waiting. We're just going to wait on the combined draft and then do an adoption call. I don't think we have to wait for it to be presented in an IETF or anything, in a formal IETF meeting or anything like that. That's my opinion.
I agree with that. So if the combined authors want to get together and try to get something out pretty fast, we could even look at doing a on the mailing list adoption call before the next IETF.
Okay, thank you. But we may be ready just a few weeks before the IETF, so I think it's okay to present the new draft. But thank you for the offer.
Yeah, I think, Bruno, that the submission deadline I checked yesterday, I think is October 25th. So I think we're gonna try to make that. You agree?
Yes, I agree.
Okay,
But
so
not 4 weeks before.
I think that's today almost.
Yeah, absolutely. So I was saying that we can wait we can wait for the next meeting.
Yeah. But as far as the working group chairs, anything you can do to accelerate the working group adoption process from the point of view of us authors, I think is most welcome.
Yep. Great. Okay. AC, do you have anything else? It's a pretty successful interim, I think.
Yeah, no, I think this is good, and the good thing, this is the best possible outcome. To have a combined draft, because then there's a better possibility of the different tools, there being discussion of them working together as well, as opposed to having two independent tracks.
Yep. All right, everyone. I guess that's it, unless anybody wants to pop into the queue. Going once, going twice, going... Aizen. You're up.
You can unmute and speak, Arjun.
Hello?
Yep.
Hello?
We can hear you.
Yeah. Sorry for interruption. I want to ask when will we start our PUA draft adoption call? We have asked the essay and question several times, and we think this draft has been discussed intensely on the list, and we have updated the draft according to the comments. So it is time to initiate the adoption call.
AC?
Yeah.
I think we can address that offline. It doesn't have anything to do with this. We have to, there's some technical issues I think we should discuss a little bit more. And whether we do that before or in the context of an adoption call is a question too. But I don't think it needs, it's relevant to ISI flooding optimization.
Yeah, I mean, since we have time, if you're looking for an update, AC and I just spoke about the PUA draft yesterday. So it is on our minds, and we want to go back and look at what was presented recently by Peter as well. But I think, you know, you're making a reasonable request. It's been around for a while, and we're going to have to put it up for an adoption call, I think. So let us just circle back to that over the next few days and get back to you. Okay. Okay, great. Anybody else want to beat us up?
Any other drafts that need adoption calls?
Right. Okay, well, thanks everybody. Great outcome, and see you at the next virtual IETF. Thanks a lot.
Everyone.
All right, I captured the jabber too in case you want to put that in the minutes. All right. Bye, everyone.